Hello everybody, my name is Victor Abreu.
Ted Schreiber.
Hisham.
Brandon. Matt Dietlich. And Quincy.
Okay, today we're going to be talking about sensors and their application in the modern robot. We're going to be giving a brief introduction about the types of sensors that are used in robots, and then we're going to dive deeper into the specific type of sensor that was used in our project, the rangefinder. From there on, we're going to explain the different types of rangefinders that are available in today's market and how they work. And then we'll specifically talk about the rangefinder that was used in our project and how it was programmed in the microprocessor. From there on, we're going to give a summary that's going to briefly explain the concepts and material that we covered in today's presentation. At many times, or at most times, you want your robot to mimic human actions, reactions, and senses. You're going to want your robot to be able to see its surrounding and understand its surroundings so that it can target and track an object. You're going to want a robot to understand its current position and its orientation in order to develop a control system so that you can control its movements. Like humans, you're going to want a robot to be able to actually go into an area and understand its surrounding so that it can use that and save that and remember that and use that for a future time. There are sensors that are able to detect specific sounds or any sounds emanating from an area. You can apply a sensor onto a robot so that it can feel when it comes in contact with another object, such as collision detection. NASA uses temperature sensors on some of the robots to send over to Mars in order to detect the temperature, humidity, the level of oxygen, carbon dioxide, amongst other things. In general, it's safe to say that depending on the application of the robot, sensors are needed and are utilized in order for them to complete a specific target. Now to speak specifically about the rangefinders. Rangefinders are the type of sensors that are used to detect the distance between one object and another and the sensor. Now, their applications are vast and they expand out to many different types of things such as collision detection, where you'll find that in vehicles such as the Lexus IS350, all the way down from your household applications such as motion sensors, where you can find those inside your homes or in front of your lawns, those type of things. You can find them in manufacturing facilities, where they'll be testing quality data such as the length and width of an object. As mentioned before, you can use them to actually physically map a surrounding area and use that for a future time. You can even find these types of sensors in sniper rifles or other types of tools that will be used in hunting or military applications. And from here on, I'm going to let Hisham talk about the rangefinders.
So there are many types of rangefinders. I'll specifically be talking about the reflectivity sensor. XP will elaborate on the laser. Matt will be talking about the radar, and Ted will be talking about the ultrasonic. So reflective sensors use an infrared emitter that is adjacent to a phototransistor. And when an object enters the range of detection, the infrared is going to reflect back into the phototransistor. Now, this change in energy that is on the phototransistor is used to emit a current that is used as an input signal. And the higher the energy that hits the phototransistor, the higher the current. Also, the time it takes for the infrared to bounce back the object can be used to measure the distance. Now, there are many applications for this type of sensor. As I mentioned earlier, the object detection. The other one is line following or wall tracking. And this is done by comparing the infrared signature of the object to its surrounding or background. So if you take, for example, a spider that's walking on a wall, it emits a certain signature that is different from the wall, and that allows us to detect the movement of the spider. Another interesting application is an optical encoder, which is made of an infrared sensor, a phototransistor, and a rotating disk in between. Now the disk is etched with certain patterns, and as it rotates, these patterns interrupt the signal that's going to the phototransistor. This can be used to emit a digital signal or a pulse wave. Now there are drawbacks for this type of sensor. One is that it requires direct line of sight, which means we can lose the object quite easily. And the other is that any intense light can cause an interference. Now, these have a small range from 0 to 80 centimeters, but they are quite cheap. As you can see, they range from $2 to $10.
Okay, laser sensors, how does it work? So basically it sends out a laser beam that will hit the target, and the sensor will measure the time for the beam to hit the target and come back to the sensor again. And this is called the time of flight principle. And after the sensor gets the time, it will use the equation d equals to c times t divided by 2, where c is the speed of light, and to calculate the distance of the sensor from the sensor to the object. And one drawback of the laser sensor is that it's not made for sub-millimeter measurement. Because if you're going to measure a sub-millimeter distance using the laser sensor, the time has to be really, really small, and that time might be too small for the sensor to pick up. And one application for the laser sensor is HELMD, which is a self-driving truck for military use. And it has a laser sensor on top of it, and the sensor will spin at a very fast speed, and it will scan the surroundings of the truck and plot out a 3D map for the onboard computer to calculate the best route for the truck. And I will let Matt to talk about the radar sensor.
So radar stands for radio detection and ranging, and it uses radio waves to detect the location and speed of objects. A radar sensor is made up of a transmitter and a receiver, though they don't have to be in the same location. The basic way it works is that the transmitter will send out periodic pulses of radio waves, and objects will reflect a small amount of energy back where the receiver will pick it up. Metals, seawater, wetlands, pretty much any electrically conductive material reflects these radio waves really well. So the power returned equation that's shown depends on a few things, such as the gain in the area of the antenna, the strength of the original signal, the scattering coefficient of the objects that are reflecting the radio waves, and the distance between the transmitter and the receiver. Radar is used for long-range sensing because the energy that it produces isn't absorbed by a lot of things, as opposed to light or ultraviolet light applications that won't work well in fog or heavy weather conditions. That's why aircrafts use radar almost solely when landing in heavy weather conditions. So radar also uses a range of frequencies which allow for longer range applications or higher resolution applications. The 3 to 30 megahertz range allows long range sensing, and that corresponds to a wavelength of between 10 and 100 meters. The 12 to 18 gigahertz range is used for higher resolution applications, and that corresponds to a wavelength of 1 to 3 centimeters. Some real-world applications of radar are in air and missile defense, meteorology, and ocean surveillance. I'll let Ted talk about this, the sensor we're using.
Okay, yeah, now onto the sensor we're using for our project, the ultrasonic sensor. Pretty much how it works is it emits a quick pulse of ultrasonic sound at about 50 kilohertz, which is well above the audible frequency for humans. And with the known propagation speed, what it does is it measures the amount of time that it takes for the pulse to hit the object and come back, and then with velocity and time, it's easy to calculate distance. These ultrasonic range sensors can measure distance up to a pretty good length, about 30 meters. Unfortunately, though, they do have a dead zone close to the front of the receiver. It cannot measure objects that are less than 1 centimeter. They're also pretty affordable, normally in the price range of $15 to $50. Apart from the dead zone right in front of it, there are also a few drawbacks. The first thing is that there's a 30-degree uncertainty, meaning that anything within a 30-degree cone of the sensor will trigger the rangefinder, even if that's not the object that you're looking to detect. Also, for distances of up to 30 meters, it takes 30 meters to get there, 30 meters to get back, a total of 60. That can take up to 200 milliseconds, which if you need something really fast, that can be a sizable delay. There are many real-world applications for the ultrasonic sensor. The first one, I'm sure you guys have all heard, the ultrasound, which doctors use to help look inside the bodies and see what's going on. They're also used in automated factories and assembly plants. Used to measure the size of things to detect defects. One of the great applications for them is clear object detection. Stuff that uses lasers cannot measure that because if you're trying to measure, say, a piece of glass, the laser will go right through that, whereas the ultrasonic, using sound waves, will bounce off that, and you can still measure that just fine. And then also there's the liquid level measure. So it can measure like the amount of liquid in the seal barrel.
All right, so the sensor that we ended up choosing was the Devantech SRF05 ultrasonic sensor. The three main reasons we chose it was, one, it was extremely compatible with our Arduino Uno. Lots of people have used these two together. Relatively low cost, it was around 30 bucks. That's pretty cheap, right in the mid-range. There's actually two modes of operation that I'm going to talk about. They both essentially do the same thing, it's just the user preference. Mode 1, which is this one, is the easier of the two modes. It uses two separate I/O pins. So first you have your trigger pin, then you have the echo pin, which will measure the response signal, as well as the 5-volt power supply and ground. And then the fifth pin is the mode determining pin. In this case, it's empty, so there's no connection. And then these pins are the programming pins, which are used by the manufacturer. It's important that you don't hook them up wrong, otherwise you can burn up the sensor if you hook up these over here. They made that very clear. So here's a timing diagram for mode 1. So since there's two separate echo and trigger pins, when the user triggers the sonic burst, that's will occur here in the third pin. And then the ultrasonic burst, the 8 cycles will pulse out, and then the echo pin will measure the time until the response is detected from bouncing off of the object. After a certain time, it will time out, and I'll just give an infinite output on the controller. So mode 2, this is the one that we ended up using. What it actually does is it combines the trigger and echo pins, so it's a saving measure. So in this case, we've still got the 5-volt power supply and the ground, but in this time, the trigger and echo are both connected to 3. And then the mode pin that was empty in mode 1 is now connected in parallel to ground. And that can be shown here in the timing diagram, where you see that the trigger and the echo are both on the same pin. And then this is, again, the sonic burst that is sent out. All right, so this is the basic wire diagram that we had. We used the Arduino Uno for our microcontroller. It did need a 7 to 12 volt power supply. And you can see here that for mode 2, this is the mode pin and the ground pin. They're connected in parallel, and then that's connected to ground. And then the trigger and the echo pin are combined, and that goes up to pin 7. So in our case, we had multiple sensors, we had a webcam, so we needed lots of I/O pins, and if there's 14 available, if you use 2 per sensor, those adds up really quick.
Okay, so this is the Arduino code for the ultrasonic sensor. And so, as you can see, maybe too small. We first specify the pin number for the ultrasonic sensor. And after that, we start the communication of the Arduino board and the sensor. And then we tell the sensor to send out the pin by giving the sensor a high pulse for 2 or more microseconds. And to give the sensor make the sensor send out the clear pin, we send out a low pulse before we send out the high pulse to make sure the pin is clear. And after that, we use the same input pin to read from the sensor to get the time of the pin from the sensor sending out that and echo it back from the object. And on the last part of the code, we use that time we got from the sensor to calculate the distance of the from the sensor to the object, and we print it out for debugging. And that's the code for the ultrasonic sensor.
So in summary, we talked about the types of sensors, the reflective, the laser, the radar, and the ultrasonic sensor. We talked about the application of the range finding sensors in our project, the Devantech SRF05 ultrasonic sensor, and how you interface that with the Arduino Uno. And we also talked about how to utilize programming to perform distance calculations and using it for our robotic motion and collision avoidance. And that does it for our presentation. Thank you.
Are there questions? I have one. When you use these ultrasound sensors, how sensitive are they to the different types of material that the sound wave bounces off of? Say, I can see, a brick wall that bounces off real easy. If it's somebody with a sweatshirt on that absorbs sound and stuff, have you noticed the difference, or is it sensitive to that?
Not that we've noticed. I mean, we probably can look at that more. But the measurements that we've tested on, they're all pretty accurate, just by visual testing. So I'm sure there is a small difference, but not that we notice.
Other questions? If not, thank you.